are indigenous. I started with the people that I knew, which was those with a doctorate degree. And we've identified through sort of word of mouth 51 people from Australia, across the Pacific, and North America who identify as indigenous and have a doctorate in math, across math education, applied math, theoretical math, statistics, and biostatistics. And where I'm starting to expand that network to those with masters, bachelors, and teachers, and just loosely how you would if you identify as both mathematicians and indigenous. So if anyone knows people that could benefit from this network, because we like to just put faces, because we come in all different faces, so that students, aspiring mathematicians, if they just want to see, they think they don't belong there, they can go here, they can see people that look like them. And also tell their stories. So if you are interested, please feel free to contact me. And the website is indigenousmathematicians.org. So with that said, also, as like the first native Hawaiian to get a PhD in math, I thought, that's great. I come back to Hawaii, can teach the people that, that I grew up with, but yet I didn't have any training on mathematics that was through my own culture. People ask me, "Oh, you must know like ethno-math," and I'm like, "Well, no, I just know math." and I knew math well, but I didn't know like math in a cultural component. And it was right at the start of the pandemic, an NSF grant that we had. We had a workshop to create or to help our STEM faculty at UH West Oahu put more cultural relevance into our STEM curriculum. And this was led by Walter Kahomoku, and his framework was from Keiki Kawaiʻaia. And through that, I'm going to sort of share my journey from there. And the stuff that I'm doing is I'm sequentially releasing it. The website's not fully ready, but if you do want to see some of the things, it's kamuelayong.com/trigonometry, or the QR code looks way smaller on the screen than it did on my computer. But kamuelayong.com/trigonometry. I hope that's easy enough for you. Okay, so I'll begin. The way I reimagined my trigonometry pre-calculus course was I thought of it as a big concept. How do I want to tell the story of this class? How do I want to tell the story of trigonometry? And for me, the big concept was navigation. So we start with a big concept, and then the intent. What is it that we're trying to do? And this is to understand the relation between trigonometry, navigation, as well as our everyday lives. And then under that, we have the content and skills. That's the stuff that we put in the syllabus. What do we need to teach? Compass, angles, direction, movements. Those are the more specific parts of what we're doing in this class. And this is further broken up into different units of my course. So I looked at the different units. The first unit was really just the intro to trig functions. Okay? And in that, the big concept was for my students to understand a compass, angles, and just triangles, just the basic thing. Now, the intent is like, how do angles and triangles, how are they related to trigonometry? And then the content and skills. This is to understand quadrants, angles, and how they're relative to different quadrants and so forth. And students will be able to understand how a triangle is used to solve problems. The next unit, this is applications of trigonometric functions. We did similar things. The intent was how to use trigonometry to analyze triangles and apply it. Contents and skills, trigonometry of right triangles, inverse trigonometry, law of sines, law of cosines, and so forth. Unit 3, this is sort of more of like the analytic trig, and I didn't find a whole lot of ways to relate it, so I sold this unit as us building our toolbox. Now that we understand trigonometry, we need to know some tools to do things. Those involve like half angles, double angles. So we're just I can't quite make direct relations with everything, but I can say, we're building the toolbox that we need to do something in the next section, or to answer some problems that were posed earlier. And then the last section was, this is the polar vectors, parametric equations. The big concept with those topics relate to direction, movements. The intent is real-world applications on using polar and vectors. So polar means like you go to an angle and you have a distance, right? That's usually how we get to places. We don't say like, to get to that side of the room, well, actually the way things are configured, but I would take, 10 steps to my right and then 15 steps forward. I would just say, no, I go here and you go that way. So make things more relatable to the real world for that. Now my students, what do students want to know? They're always asking why, right? They want to know a lesson that can touch their heart, that they can relate to. And so the hook, like what is the hook that the learners want? And this builds upon prior knowledge that they have and the strengths that these students are developing. Now, what are we doing? The content and skills. This is the direct instruction that, standard teaching. We're utilizing a variety of instructional strategies. How are we doing this? We're applying and practicing what's the things that we're taught. Hands-on activities, things that they can relate to. And then after they learn, what now? Like, why did we do this? So they can create a project, a showcase their new skills and knowledge. So I'll walk you through some of the things in here, and we won't go through like the whole course, but I'll walk you through certain examples. So back to like Unit 1, Intro to Trig Functions. Now, when I started this, I had no idea what I was going to relate trigonometry to. And I was trying to think, like, what do I know, like, culturally? And I didn't really have much. And I thought, well, I knew, like, two things. And I'll tell you when I hit those two things and then how it went from there. But so intro to trig functions, why are we doing this? The lessons that touch the heart and spirit. That is, show that there's relevance to, like, the Hawaiian star compass, if anyone has heard of that. The Hawaiian star compass, right triangles. What are we doing? So we are teaching them how to read the unit circle. So I will show you how the star compass is very similar to the unit circle. We're applying it. Students will build their knowledge on trig by working on application problems, as well as things like installing solar panels, looking at how sand moves on a beach, and they'll calculate if we're trying to go in one direction, but we get blown off course, how far off course do we actually get blown off? And then what now? They'll make their own compass, their own compass unit circle, and work on these things. So the Hawaiian star compass, this is one of like the two things that I knew about navigation before embarking on this project. I knew that the Hawaiian star compass had a lot of symmetry. A lot of things from one place to another were the same. So if we look on here, we have they call it how the houses. This is house law. So just above the east-west law, and if you go on the left side, all the way on west, is also law. And you go down by one house, law and law. The unit circle has a lot of these same things. I would be teaching unit circles, and I get the end of the class, end of like the semester, and then students finally go, wait, it's the same like throughout. Like, why did you? They see this big circle and they get scared because the circle can be intimidating. But in the circle, if you go up from the x-axis by 30 degrees, the trig function, let's say sine of 30 degrees, is going to be the same as if you go up from the left 180 by another 30 degrees. So 180 minus 30 is 150. So sine of 30 in the quadrant 1 is the same as sine of 180 minus 30, or 150. Or if you go down by 30, so 210. Or if you go around 360 and go, so 30 degrees, sine of 30, sine of 150, sine of 210, and sine of 330, they all have the same trigonometric value. Just like how we name the houses in the Hawaiian star compass. Once they realize this, they're like, wow, like, it made it a lot easier. And before that, students would go the whole year without knowing this. And now they can understand it right away, like in that first lesson. No matter how much I tell them it's the same, it's not the same to them, right? 30 degrees is not 150, it's not 210, and it's not 330. 30 degrees is 30. And so they just like, they can't comprehend that. So when I show them something that's related to maybe not math, that they can understand. So there are similarities. So when I talk about similarities, I had mentioned quadrants, right? We have quadrant 1, 2, 3, and 4. That's what we learn in math. Now, you can also just talk about quadrants by looking at, like, here's the ground and, like, here's a tree, right? The tree sways, like the coconut tree sways on the ground, but the tree is not just planted on top of the ground. If it blew, it would fall over. What happens? The tree has below, there's roots that go below. So whatever's above, there's like the opposite force holding it down. So you can talk about just the quadrants that way, or how the axis works. In the star compass, our northeast quadrant is called Ko'olau, named after the winds that come from that direction, the northeast winds. Ho'olua, the northwest, Kona, the southwest, and Malanai, the southeast quadrant. So we have 4 different winds, or 4 different parts of the star compass, 4 different parts of our our Cartesian plane. Now there's symmetry. Now this is where the symmetry, how the students really grasp that 30 degrees actually is 150, or at least sine of 30 is the same as sine of 150. When the sun rises, I lost my orientation, but where the sun rises in the east, and it comes over the sky, and it sets, it will set in the same spot. Or any star, when they rise, and we may have seen these like time-lapse pictures of the stars going over in that circle, where they rise, if this is where we are and we look where they rise in the horizon, they don't all rise just east, right? Some of them rise a little bit further, north of east or south of east. And so as they rise, wherever off the east-west line they rise from is the exact same spot where they'll set. We have that symmetry. So the way a star rises, and that is similar to symmetry about the y-axis. We also have, if you're on a canoe and you have wind coming in, or currents coming to you from one place where it exits, it goes in the same direction. That's symmetry about the origin. So we start relating just these concepts of symmetry to a physical being, the physical realm, things that all humans, all children, when they're young, they're curious, they're looking at things, they're observing, they're like, oh, the wind's coming here, or they can see all those stuff. And so we all have it in us to recall back when we're just observing the natural world around us. Tying into that, it all of a sudden makes it a lot easier for students to do that. Now, what do navigators know? This is taken straight from the Polynesian Voyaging Society's website, Hokulea. And if you're sailing in one direction and you get blown off by one house, so they align themselves every night when the sun sets and the stars rise. They align themselves after one day, and they realize we've actually moved one day off where we're supposed to be by one house. They know, they have this memorized, that they are now 24 miles off of their reference course. So they have this memorized, but what is this? This is a right triangle. These are things that I looked on their website, and I found that. So this is the example. You're going for one place, and navigators have that in their mind. So I tell my students, the navigators are doing this. And I was talking to a navigator last night. He says, I don't have any good math. I'm like, well, you're actually really good at math. I'm just writing what you have in here on paper. I've deviated this far. I need to compensate in the next couple of days going back and so forth. So they have that down, and I'm just explaining it in a way that makes things relevant. I'm gonna just kind of skip through some of the things. Inverse trigonometry. Now, what is inverse trigonometry? I began by giving a little history lesson, telling them about how Hawaiians learnt trigonometry through people of Satawal, and how the other people in in a Yap and Chuk, they have kept the knowledge of voyaging or of navigating. It hasn't been lost. And so we learned it from them, what we know now. So I talk about this, that we learned it from them, and then we gave them this gift as a thank you. And we're bringing this large canoe to this island that's only 1 square mile. So I'm just telling the story. Now we know we need to set on the map, our first leg of the journey is 1,000 nautical miles. We have to go to the east, and then 500 nautical miles to the south. Now, up until this point, we know trig functions with a known angle. Now we don't know the angle. How do we do this? Like, you can't just divide by the word tangent. Like, that's not, which is what we see all the time. So I have to now say, this is an inverse trig problem. And then once I hook them, then I talk about inverse functions and then inverse trig functions and then we go through, and now we know the angle, we know where to sail to. Another example, and I have a video on YouTube. It's a quick 2-minute teaching demo if people are interested, but it's finding land. And so I put students into the mind of the navigator. I say, we're sailing to Rapa Nui. And as we're sailing to Rapa Nui, the navigator knows they're getting near by the stars. The stars tell us what latitude we're at. They also know through a process called dead reckoning how far they've traveled. So they know how far they've traveled. They know what latitude they're at. Then they look at other things. And those are all based off of speed, direction, wind, and all those things. But they know they're near. They start feeling for the refraction of waves coming off of an island. They look for vegetation that might have drifted. Land-based seabirds. So if we see a small white bird out, over here in Honolulu, it's called the manu oku. They nest at night. They go out to sea, then they come back. So if you see them, you're within their maximum traveling length. So you'll be near. So I'm telling our students what the navigator, putting them in that mind. And then I say, so if you're on the deck and your eyes are 9 feet above water, when do you first see that land emerge? So now I finally actually go into math. This is what the math looks like. We see, it deals with triangles and angles and whatnot. As we, on the bottom, as the island is getting closer, you can see the island lifts up over the horizon. We're pulling the mountain out of the water. So that's what's happening, in the navigator. This is the math, because they want to know, when do I see it? Because if you're sailing, you're near, you start doing this sweeping motion, and if you know how far you can see, you don't want to make too big of a sweeping motion, and it'll be if the island is here and you sweep and you totally miss it. So you want to make a tighter one if you know what your what your vision is. So that's the finding land, and I do on YouTube, I think the same words, inverse trigonometry, finding land, Kamuela. It's there. Variations of this. How far can you see from each island? Or when can you see the highest point of each island? Mauna Kea, the largest mountain, over here is about 120 miles. You can see it over the horizon. So, if you go on Oahu, you go all the way on the east side, how many islands can you see? How far can you see? What about if I went up at a different elevation? Which islands can I see from there? We do that in my class. So for that, this is at Sandy Beach. You can see over here, there's islands that are just over the horizon. Now, that theoretical one is a pinpoint right on the horizon, right? So if you have all that ehukai, the ocean spray, you're not going to be able to see it. But, this kind of might give you an idea. Here's Maui is over here. We got Molokai. So you can see some islands, and just, for reference, that would be over here. Honolulu, we're over here. So we can see which islands. We can't see the big island. We can't see Mauna Kea. It's just over the horizon. But if we go up high enough, we can see it. So if we go on the mountains, again, where am I? Right, just parking lots and then hallways where I don't see, where I don't have windows, I get very... I know how to get out of the building, but I don't remember, where. A variation of that is, now, I know where my horizon is, but can I also see, how fast can you see the sun rise from the horizon? Because it's just that same ratio of how far the horizon is to the circumference of the earth is the time that you see the sunrise before someone at sea level over 24 hours. So this whole problem was inspired from a textbook problem that just said you're in Maine, you're the first point east, you're on the top of the mountain, you see the sunrise before anyone else in the continental US, how much faster do you see it? I said, well, that's cool. We got bigger mountains. Let's do that. And I said, wait a minute, instead of from the top of the mountain looking out, what about if you're on sea looking at the mountain? I took structurally the same problem and I just changed it. Similarly, the next section, we talk about inverse functions. Now we know what angle to sail to. And then I say, I forgot to tell you, there's a half knot current. So if we sail that way, we're gonna miss the island. So now it's not a right triangle. We have to compensate. We don't know the tools for non-right triangles. Introducing law of sines. We talk about that. So that's sort of the how we go through this. This is what it looks like. We don't know oblique triangles. Law of sines will answer that. I talk about vectors. Now the only other thing, I'm getting low on time. The only other thing that I knew about navigation before this is that latitude sailing, we know how far north-south we are, but we don't know how far east-west we are. Because the stars were always moving east to west. But as you go further north, the stars go at different angles. And so the North Star always points north, but mathematically you can show that your latitude is the same degree from the horizon that the North Star is. But there's a bunch of other ways to tell that, and the angles that the stars take change based off of your latitude. But I knew latitude sailing. So going from Tahiti, our ancestral highway, they would go sail north till we hit the right latitude of Hawaii, and then we'd go west. Because if we tried to sail directly to Hawaii and we missed it, like we wouldn't know if we landed too far west. We just know like we're at the right latitude. So if you know you go straight up and then you go west, then we were like, okay, we know we're gonna hit. That's the only thing I knew. This is the sum of vectors. I introduced sum of vectors that way, going from point A to point B. It's the same as, if some of you flew in, if you didn't take a direct flight, how did you get here? You had a connecting city. So from your hometown to the Ala Moana Hotel, you took a couple of different paths, but the sum of those vectors was from home to this room right now. That's what the sum of vectors is. This is the standard textbook of that. I end up having my students create a charting. This right chart is based off of an actual navigation plan that Hikianalia sailed from Tahiti in 5 years ago, coming back from the Malama Honua Worldwide Tour. So I go through that, I show my students, and I was on a plane. I took pictures of some textbook problem. I was on a plane reading problems. Oh, yeah. Thought you were trying to kick me out.
No. You can stay as long as you like.
I just took some problems. I was just reading. I get a lot of inspiration from reading textbook problems. I was reading this, and I saw, okay, they're building a roof. We know how far the ridge line of the roof is. We know, these dimensions. What's the angle of the roof? Okay. I said, well, that's okay. That's not a bad problem, but let me take this as an opportunity to talk about indigenous architecture. Part A, in fact, the Seating County of Honolulu has building specs for the kauhale, for a traditional dwelling. Across the Pacific and other indigenous cultures, there's lots of variations. But I can use that Part A to just talk about, in this culture, this is the name of this dwelling, this is the purpose of it, and this is the specifications. How far is the ridge line and how high is it, or what's the angle, and they all have different purposes. So I can use just this problem and turn it into something that's a little bit more interesting. Again, I'm not changing the structure of the problem. I'm just changing the lens that I look at it through. And then one problem, and I'll just end with, I'll end with that, is angular velocity. You take a child has a rock on the end of a string and they're spinning it around their head, and how fast is that rock moving? Or a similar problem is like a point on a tire on a wheel is spinning. How fast is that plate moving? I'm like who really, like, really? And one day I was out on the canoe and I was working. I had to really spin the steering paddle, and my arms were so sore. And I go, wait, how fast is that paddle moving? Let's just write about that instead. So I videoed myself, and I to like see like how far like the radius was and what my speed was. I only did it for 20 seconds. Before I told him to stop filming, because I'm not gonna find my RPMs like and do it for a whole minute. I said 20 seconds. Okay, good. I can extrapolate from there. But so I found that and I put that in, and then I was working with teachers, and they actually outsourced it to their students. They said, is there something that we do that like you can swing something around your head? And they said poi balls. So in Maori in New Zealand, the women one of their dancing is they have is poi balls, and they spin it around. So you can talk about that because their students were dancers, or one of their students was a dancer, and so everyone could relate to those things. So just understanding the structure of a problem, even if like you can't come up with it. And that teacher, she was from Europe, teaching, but was able to get this native Hawaiian cultural example through just working with the students. And so if you just have like one new example a semester, and you can build your own toolbox and outsource it to students, make it a project, and pick the, good ones that are good to perpetuate. But I didn't really know much, and I started off with this not having anyone in my family being on canoe people. Okay. Somewhere along the line, to get to Hawaii, I had an ancestor that was a canoe person that got me here. Okay, but like nowhere in my immediate family there was people on the water, and so what I did was I didn't want to be an outsider talking about this culture, even though I am Native Hawaiian, but that like my current culture is not that. And so I volunteered with Kanihuna Moku. It's a voyaging society. They take children out on the windward side of Oahu. I got in this space. I got to see, because that example of when do you first see land, the first time I did that is I said, you're going to Tahiti, but in Tahiti, you're actually going to hit atolls. You're going to hit atolls way before you see the land. But that was a mistake that an outsider would know. So I went in, I immersed myself, I talked with the community, I was welcomed in the community. In fact, today, Va'a Festival, they have canoes from all over the state. Yesterday, a canoe from Maui came in. That's where my son and I came to greet them out on the water. Hokule'a just sailed around this morning. If you're up at like 6 a.m., you would have seen them going around Diamond Head. They're in Kualoa right now. And so this is me with one of the left picture is me just working with kids, getting myself in that space, seeing, now I'm here, I can see connections through K-12 and beyond, all these other things, not just for myself. I only knew two things before coming in here. I learned from the more academic, learning about navigation, but being in the culture, learning with these people, talking story. Like I was there last night, talking with navigators, talking with crew members. Is this really like accurate? Do they do this? So that I'm part of the community working, because not all things are to be shared. Like, for example, hula is not something that you should share about without express permission from like the kumu hula, from the person in charge. Different cultures have different belief systems. So it's great to indigenize our curriculum, but some people are more, it holds a more value to how it's disseminated, how it's shared. And so that's my biggest thing, is that I learned, I wanted to be part of this community in order to talk about it. And that's what I did. I spent my time volunteering, going out on the water, which, I mean, it's a perk. I kind of like it, being out on the water, like, oh, I'm so sorry, I have to miss the division meeting. I got training, so, but it's being accepted by the community, working with them to do this. That's what I did. So again, parts of it is online. We're going through the process of trying to peer review an OER book, an open education, making it free, which there's really no way of peer reviewing or no known way. So we're kind of making up the process with my librarians on getting it peer review. We're sequentially releasing things. But if you have questions, you want samples of the book and of other curriculum, please email me. The website is kamuelayong.com/trigonometry, kamuela.yong@hawaii.edu, or just look for me. Thank you.